Hey guys. Good morning. So, right off the bat, I'm not late this time. I'm so proud. Every day better. But are you working on some other class's project right now too, or no? Is this just strictly math time at the moment? Not watching a TV show, not doing a project, maybe, or is it just math? That's awesome. Love to hear it. My stream's been really weird today. It's been cutting in and out, so if it goes out, I apologize. I'll try to restart it if it does, but just know it's been finicky. But we'll see. Luckily, we don't have too much to go through again because we went through most of this lesson yesterday, and then so the rest of today is just kind of finishing out those last couple problems, and we'll be good. All right. Well, hello to everybody here. Let's cut back and see where we left off. So we talked about the Richter scale and how we can use it to measure earthquakes and the magnitude of earthquakes, all right, which is this lovely formula. And we also talked about how to measure how loud a sound is, okay, which is in decibels, and the formula for that, which is near identical to the Richter scale formula. The only difference is we have a coefficient of 10 here, but otherwise quite similar. We did a couple basic examples where we just had to plug in values and get the rating. So for example, this earthquake was 5.3 on the Richter scale, or we just plugged in and found that this the conversation, this sound was 49.5 decibels. All right, just a basic calculation. But we then went on to a slightly more complicated version where we're wanting to know how many more times intense, right? So we started off with knowing the two values of the earthquakes, so a 7.1 and a 6.3. We found the difference between them, which is 0.8, and then we set our equation equal to that 0.8. So then we solved for what is the ratio of the intensities. So we determined that first earthquake is 6.3 times more intense than earthquake 2. Same thing basically, but for the sound and decibels formula. So we started off knowing 95 decibels, 65 decibels, and it was just trying to figure out how many more times intense is one than the other. So find the difference between them, and then we set our equation equal to that. And then it's just solving. So once we do that, we got, in this case, the ratio equaled 1,000. So the motorcycle is 1,000 times more intense than the sound of the lawnmower. So just kind of a quick recap there. But now for us, let's go then to our kind of last type of word problem that we'll see at least, and thinking about it slightly differently. All right, so sticking with the sound though, a blender is 60 decibels and is 63 times more intense than a phone that is ringing on high. How many decibels is the phone ringing? Okay, so I know some information. I have blender 60 decibels. I'll go ahead and write that down. The phone I don't know how many decibels that is. That's the whole goal, right? The question at the end says how many decibels is the phone ringing? Okay, so we can figure that out by let me look through here. Okay. We can figure that out by using this other piece of information we know, which is that the blender is 63 times more intense. Okay, so what that means is if I compare the ratios, so the intensity of the blender, if I were to divide that by the intensity of the phone, I would get 63. And yesterday I showed you how we actually started off that by writing that as the blender is 63 times the intensity of the phone. And that's fine to think about it like that. So then we just divide that intensity of the phone on both sides and we end up with this equation right here. Right, the ratio between those two intensities is 63. Okay. So let's take a look. Well, I guess not magnitude. So let's use our formula, but let's compare these two sounds together. Okay, we talked about that yesterday. We can compare to the threshold, which is the smallest detectable amount, or we can just compare any two sounds or compare any two earthquakes. Right? If we put those together inside the logarithm of comparing the ratios of the intensities. All right, so if we do that, we would get, so we already know that that ratio is 63. This is one heck of an equal sign. Let's try again. Still ridiculous, but whatever. So 10 log of 63. I lost my calculator. Found it. Don't worry. You seem worried. Stop worrying, you guys. You can't live your life like this. Quit worrying so much. 10 log of 63, common log, is 17.99. So since we're rounding to tenths, I'm just going to round that to 18. Now remember, in our formula, we looked at the ratio of the intensities. So what that means is this is not my answer per se. I'm going to use it to find my answer. But what it means is this value that I get here, this is the difference this is the difference in decibels between the two. Okay, so let's go back to the beginning. We know the blender is 60 decibels. The phone is, we don't know how many decibels, but we know it's less than the blender. So I'm going to take 60 and subtract 18. Right, and so what is that? That's the phone. So the phone ringing is 42 decibels. Right, and we subtracted 18 because we know the phone is softer sound than the blender. Right, the problem straight up tells us at the beginning the blender is more intense, so the blender is louder. Great. So I know the difference between the blender and the phone is 18 decibels. So we just we'll have to think and decide. Well, wait. So should we add 18 or subtract 18? Well, the phone is a softer sound, so we'll subtract 18. So my final answer 42 decibels for the phone. All right, let's look at this next one. So very similar. Earthquake 1 is a 5.0. All right, so already I'm just going to write that down. Earthquake 1, 5.0. 141,000 times less intense than earthquake 2. What is the rating of earthquake 2? So earthquake 2, we just don't know what the rating is. Oh, get the hiccups. What is the rating? We do know, though, this blue part that I've underlined, 141,000 times less intense than earthquake 2. So intensity of 2 divided by the intensity of earthquake 1 is 141,000. Now, notice that I put the intensity of earthquake 2 on top. I mentioned this yesterday in that we always want the stronger of the two intensities to be on top. Okay, so whether that's the larger earthquake or the louder sound or whatever it is, okay, we want the more intense thing, the louder sound, the greater rating, whatever, however you want to think about it. That should be what is on top. And so in this case, it tells me earthquake 1 is less intense than earthquake 2. So that's why I'm putting the intensity of 2 on top. All right, so we'll use our formula, common log of intensity 2 over intensity 1. So that's common log of 141,000. Which is 5.1. But again, let's actually think about what in the world this is. Okay, this does not mean our answer is 5.1. What this 5 point represents is the difference in magnitude between the two earthquakes. So let's go back to our beginning and decide how we should do this. All right, earthquake 2 is the stronger earthquake, right? So now, starting from earthquake 1, which is a 5.0, so when I'm thinking, okay, should I add the 5.1? Should I subtract the 5.1? Well, first off, it shouldn't make sense to subtract, because then we would end up with a negative rating for an earthquake. Okay, but earthquake 2 is stronger, so that's why I would add the 5.1. So yes, exactly, Aiden. 10.1. So we'll do 5.0 plus 5.1 equals a 10.1 for earthquake 2. which is just absolutely horrifying. I don't know if you remember back from our chart. Anything above a 9.0 is considered a great earthquake, which is total destruction. So a 10 would be just complete pandemonium. It's one of those magical earthquakes that just would destroy the world, I think. Let's see. What is the largest earthquake rating in history? I used to know this when I taught this last year. I remember looking this up. So there's actually never even been one that we've measured to be a 10.1. Largest earthquake in recorded history was in Chile, 1960, which was like a 9.4 or 9.6. So 10.1, big yikes. All right, some stuff's going down. Mostly society. So that's our third way that we could, or a third type of problem that we could end up seeing, where we know one of the ratings, but we're trying to figure out the other one, and we have to use the intensity to kind of work backwards and decide what the other rating should be or how loud the other sound should be. Okay. Questions on earthquake stuff or sound stuff? Have any of you ever actually experienced a real earthquake? I've been in like really small like tremors, not even like, I mean, I guess technically earthquakes, but like when I lived in Taiwan or when I lived in Costa Rica, there used to be like, you know, tremors where you could feel things start shaking a little bit, but it wasn't like running cover. Yeah, there was one a couple years ago in Oklahoma. You could feel it here. Oh, nice. It's pretty weird. Like, I don't know. It just seems so counterintuitive, you know? Like, where our one kind of constant is that we live on the earth, and the earth is just, you know, the ground is stationary. And then all of a sudden, the ground is shaking. Your walls are moving. It's a bit trippy. Kind of goes against the whole natural order of what you assume things should be like. Okay, well, that's all I officially have for notes. Told you to be short. We just had to finish up. But so I sent out an assignment today. The front is just practice solving equations with logarithms, and the back is just like 5 or 6 of these word problems with the earthquakes and decibels. Okay, so just kind of practice using those. Again, like I said, so tomorrow morning I'll send out a review, and you can work on that. And I don't have a specific like lesson for tomorrow, I'll get on the stream and I'll just be here if you have questions about the review or if you want me to work problems from something, then I'll do that. But I don't have a specific like notes planned for tomorrow.